So I want to note that this is based on joint work with Johanne Haugland, and you can sort of find more details and more stuff in this archive preprint we'll have listed here. And so, yeah, some of you might have heard parts of this presented in other forums, but there might be, if time permits, some new things at the end here, things that we haven't presented in this way, at least before. So having said that, I'm going to just jump into talking about so-called n-hereditary algebras. So these are sort of attempts to generalize the good behavior of sort of classical hereditary algebras to higher global dimension. So they require that the global dimension of the algebra is equal to n, and they have several formal surfunctors. To be more specific, every power of the surfunctor of such an algebra satisfies, evaluated at the free module of the algebra, satisfies that it has cohomology only in degrees multiples of n. What's surprising to me, at least, that this is sufficient to get a very nice dichotomy result. So it turns out that these n-hereditary algebras consist exactly of sort of two more or less disjoint classes of algebras, namely those that are n-rep finite and those that are n-rep infinite. And yeah, since these are supposed to be generalizations of classical hereditary algebras, it should be no surprise that these are sort of characterized by sort of similar things happening with their surfunctors as in the classical case. So for the n-rep finite ones, for each indicopposable projective, there's going to be some non-positive power of the surfunctor carrying that indicopposable projective to an indicopposable injective. But for the n-representation infinite algebras, this never happens, and that sort of characterizes them. So to getting to sort of the other part of the title, we're going to sort of recall briefly Koszul algebras, and then we're sort of going to say how each of us generalize these to the higher Koszul algebras. So here we have some graded algebra, positively graded even, and having its degree 0 part being semi-simple. Moreover, we require that the degree 0 part considered as a module over the algebra has a nice minimal projective resolution. Now, nice in what way? Well, it's going to be a graded resolution, and the ith projective in the resolution is going to be generated in internal degree I. Moreover, or equivalently, if you're dealing with some algebra lambda given by equivalent with relations, you can think of these as having the property that each morphism and the projective resolution, you consider that as a matrix over the with entries from the algebra, then each entry will be a sum of paths of length 1, i.e. arrows. Okay, so this turns out to be sort of equivalent to this x vanishing condition. So here we're computing x over the category of graded lambda modules, and yeah, so the requirement is that the self extensions of lambda 0, the graded self extensions, they are non-zero only in bi-degree II or diagonal bi-degree. So if you have cohomology in degree I, then the internal degree has to be equal to I as well. Okay, so when we sort of pass to so-called higher Koszul algebras, we sort of loosen this requirement of the degree 0 part being semi-simple. Instead, we only require that it be a finite global dimension. Moreover, instead of only looking at the lambda 0 as sort of this module having good behavior, we're sort of allowing ourselves to work with any sort of tilting module over the degree 0 part. We still have this x vanishing condition, but now it's not sort of necessarily diagonal, but we allow the cohomology to be in a degree that's a multiple of the internal degree for some fixed parameter n. So this is a generalization of some work by Madsen from 2010, and that in and of itself is sort of partially a generalization of work by Green, Reiten, and Solberg. For the rest of this very brief talk, we're only going to be looking at the case where t is equal to lambda 0, though. Moreover, most of the results I'll present are sort of simplified to sort of to avoid giving like technical assumptions and just be more reasons of time. Okay, so what can you show using using these notions? Well, you get that if you have some n representation infinite algebra A having some finiteness conditions, then you get a nice equivalence between these two triangulated categories. So here, this left guy, that's the bounded derived category of graded modules over the trivial extension of A, and the thing on the right, that's for the same, but for the n+1 pre-projective of A. So the n+1 pre-projective, that's like a higher generalization of the classical pre-projective. One thing that's sort of interesting, perhaps, is that this seems to be new even for the case of n equals 1. We haven't been able to find this in the literature, and when we've asked people, we've not heard anything to the contrary. One sort of like a bit pedantic point I would sort of like to give here is that this is for very specific gradings or choices of gradings. In particular, we're going to use the grading that puts the new arrows that you get when doing these constructions, the trivial extension, the pre-projective, we're going to put those in degree 1, and we're going to sort of let the old arrows have degree 0. And so, for instance, this is like a potential source of confusion because you have the algebra on the right here, the pre-projective, it's also classically Koszul in addition to being higher Koszul, but it's classically Koszul only with respect to the grading putting all of the arrows in degree 1. Okay, so we also get some characterization results. A is n rep infinite if and only if its trivial extension is higher Koszul with respect to A. Here A is in degree 0 and D of A is in degree 1. We also have characterization results for the n representation finite side of things. For that, we're going to need to talk about so-called almost Koszul algebras introduced by Brenda Buckler and King. So these are also positively graded, but they're finite dimensional and they have degree 0 part being semi-sum. And so as all of these assumptions, you have some highest degree, which we're going to call A. In addition, you sort of require the degree 0 part to be periodic as a module, and it has to satisfy this property. So the syzygy that gives you sort of the period, that has to be sort of shifted by q plus A. And additionally, we require that even though we have these two assumptions, it must be sort of as close to being Koszul as possible in some sense. So this translates to a kind of expansion condition on a sort of limited interval. Given this, if we generalize to the notion of to the notion of higher almost Koszulity, then you get corresponding results for n representation finite algebras, given in terms of the trivial extension. Yeah, so one thing that's sort of maybe interesting here is that this last result and the one I'm going to present now are sort of special cases of a more general result in the archive preprint. But this special case here seems like it might give sort of new examples of n representation finite algebras from old ones. So how do we do that? Well, we have a self-injective lambda that's almost Koszul, and this lambda 0 tilde is this direct sum of cosyzygies of lambda 0 that are shifted. And if we take the endomorphism algebra in the stable graded category of this lambda 0 tilde, it turns out to be A-1 representation finite. Now this might give us new examples if we combine it with the result of Grant and Iyama's that says that if you have a Koszul algebra that is there's n representation finite, then its n+1 pre-projective is almost Koszul. And if you're just looking at the classical case of n equals 1, then the pre-projective of some representation finite hereditary algebra is going to have highest degree h-2, where h is the Coxeter number of that algebra. And you can get this to be of sort of arbitrarily high degree. And so by combining these results, you even just starting with like a classical representation finite algebra, you can get M representation finite algebras for M being h-2, where h-2 is arbitrarily large. And yeah, this is for the case where you have all arrows being in degree 1. But I see that I'm now sort of more or less on the time, and I'm about where I want to finish, so I think I'm gonna stop here. So thank you for your attention.